Hello again, welcome to another review session for Calculus 3208 as you prepare for your final exams. Still under the applications of derivatives, and we're looking at optimization again. And this time we're going to try and find ways to minimize the materials that we can use to construct a container. Okay, so let's have a look at this. We're going to solve optimization problems to minimize perimeters, and then we're going to solve optimization problems to minimize surface area. Let's get right down to some questions. In order for cows to have sufficient grass for grazing, a minimum area per cow must be available. Okay, so if 1,800 square meters are required for grazing, for I guess some farm or something, what is the minimum amount of fencing required to create an appropriate rectangular grazing pen? Okay, so this sounds a lot like some questions that you've done before with maximizing volumes, but it's a little bit different the way we have to approach this, so let's take a look. We're going to have a rectangular pen, of course, and our rectangular pen will have some length and some width, and it's going to have a total area of 1,800 square meters. Okay, now, in order for us to create this pen, we want to try to minimize the perimeter, so use as little length and width as we can. So let's write a perimeter equation because that's what we want to minimize. So perimeter is going to be 2 widths, 2 lengths put together. All right, so if that's the case, then we've got to find a secondary relationship so we can replace one of those 2 variables. And it's going to be the area equation this time. That's our secondary relationship. So the area of 1,800 has to be equal to the length times the width, as we know. So we can choose which variable we want to replace because ceteris, what's the right word here? All other things being equal, ceteris paribus, I guess. So L is going to be equal to 1,800 divided by W. So we'll get rid of L. So we have P equals 2W plus 2 times L, which is 1,800 over W. Okay, so we'll simplify that a little bit, and we get 2W plus 3,600 times W to the power of minus 1. And I guess we should restrict this somehow, but the width is going to have to be greater than 0, and it's going to have to be less than, gee, I don't know. We don't know how there's no limit, I suppose, to how big we can make the width here, so it doesn't really matter. So then we'll take our derivative now and look for critical values. And we don't want a width of 0 because that would give us no area. So the perimeter is going to be equal to, the derivative here will be 2 plus, negative, so minus 3,600 times W to the power of negative 2, which is 3,600 over W squared. So I need to solve this to figure out when my derivative here, P prime, is equal to 0. 2 minus 3,600 over W squared. So if I do a quick rearrange there, I figure out that W squared has to be equal to, I'm just going to subtract that term and cross multiply, 1,800, which tells me the width that gives me my optimal solution here is either the positive or negative square root of 1,800. And 1,800 square root is 30 root 2, which I think, if I check the calculator, is going to be about 42.4. Okay, so we got about 42.4 meters for our width, and it says what is the minimum amount of fencing. So we better figure out what the length is so we can get all that put together. So the length we said was 1,800 divided by that, and it turns out that 1,800 divided by the number that was its square root is going to be just 42.4. So what we should do here is, obviously, we should create a square pen, and that will give us the same volume or the same area that we need inside using the least amount of materials to create the fence. But they did ask us how much, so it's going to be 4 times 42.4, and that's going to give us 169.6. So about 170 meters of fence to create that pen. Okay, let's check the next one. An aluminum soda can is to be constructed. So it has to hold 550 milliliters of liquid. That's a big soda can. Determine the dimensions of an approximately cylindrical can, because they're not exactly cylinders, but we can approximate that here, that would minimize the required amount of aluminum. So there's two things we need to know if we're thinking about a cylinder. We want to minimize its surface area given a fixed volume. So for this soda can, we should know that the surface area is going to be 2 circles, so 2 pi r squared, plus if we unbend it, a big rectangle, that's 2 pi r, which is the circumference, times the height. Okay, so that's the equation we want to try to minimize, the surface area, but we need a secondary relationship so we can get down to one variable here. And they tell us the volume has to be 550. So we'll use the volume equation. 550 is going to be equal to pi r squared times the height. So probably going to be easiest to get rid of h here because I only have to replace it in one place. So h is going to be 550 over pi r squared. So we put all this together and we get an area that's going to be 2 pi r squared plus 2 pi r times 550 over pi r squared. And then we can simplify this equation. 2 pi r squared is going to stay there, but these pi's are going to disappear, and that r will go away with one of the r's from the r squared, and so what we end up with is 2 times 550 is 1100 over r. Okay, so there's our area equation. And how small can we make r? Well, 0 wouldn't give us any volume at all. We'd have to make it an infinitely tall container. And we can make it, I guess, as big as we want until the height gets down to 0. But either way, the endpoints of this are going to be silly, so we're only really interested in our critical values. So let's differentiate. So a prime here, or the derivative of our area, is going to be equal to 4 pi r. And if I think of this as being times r to the negative 1 up here, then that's going to be negative 1100 r to the negative 2, or over r squared. So let's solve to figure out where that equation is going to be equal to 0. So 0 equals 4 pi r minus 1100 over r squared. So I'm going to have 1100 equals 4 pi r squared. So r is going to be the square root of, 4 pi r cubed, isn't it, when I cross multiply there? R is going to be the cube root of 1100 over 4 pi. So the cube root of 1100 over 4 pi, if I plug that in my calculator here, I get 4.44 centimeters. So we construct a can that's got a radius of 4.44 centimeters. It said determine the dimensions, so we better get the height as well. So the height is going to be 550 divided by pi times 4.44 squared. And any good calculator should tell us that that's about 8.88 centimeters. Okay, so what we have here is an aluminum can that has the same height and diameter because the radius is 4.44, so we double that. Okay, let's do another one. These are fun problems. I'm having a lot of fun here. A drinking trough for horses, wow, even horses need water, is to be constructed from wooden materials, alrighty, and then sealed from the inside. The designer has decided to construct the trough in the shape of a square prism without one of its sides. So that's like a rectangular prism, except the ends are going to be squares exactly. So we've got this rectangular prism like this, only the ends are going to be squares. So let's call those squares having side lengths of x and x. And then our trough can be L units long, we'll say. So it's basically an open top box, I guess, without one of its sides, it says. So determine the dimensions of the trough that can hold 10 cubic meters of water, which uses the least amount of material. All right, let's see if we can figure that out now. So the least amount of material means we want to minimize surface area. So our surface area here is going to be, well, there's no top, but I'm going to have 3 identical or congruent rectangles around the sides. One here, one there, and one on the bottom. So each one of those is going to have an area of x times L. So I need 3 extra large. So I need 3xl for that. Plus each end is going to have an area of x times x. So I've got x squared. All right. So there's my equation, but I've got 2 variables. So I need a secondary relationship to replace my length. So let's look at the volume, because that's the other thing we know about. The volume, which I know has to be 10 meters cubed for this guy, is going to be x times L. So probably easiest to replace L here. L is going to be 10 divided by x squared. Okay, so I want to find my area equation now. It's going to be 3x times, instead of L, we'll call it 10 over x squared, plus another, there should be two of those ends, shouldn't there? Plus another 2x squared there. So that's going to give us an area that is 30 on x and plus 2x squared. Okay, so now we'll think about restrictions on that. X could be as big as we like, I suppose, and it could go to 0, so the endpoints are sort of irrelevant here. We're just going to have to check to see what our critical value is. So we're going to go with a prime, or dA over dx if you like, and a prime is going to be, so if I have to differentiate 30 times x to the power of -1, I get negative 30 times x to the power of -2 plus 4x for the derivative of x squared. I'm going to let that equal 0 and find out what kind of magic will happen. So I've got 30 on x squared equals 4x. So I'm going to get x cubed equals 30 over 4. And then I take the cube root of both sides, and I find out that x has to be the cube root of 30 on 4, which is 30 divided by 4, and cubed rooted is 1.96 I'm getting about. So about 1.96. And so then we have to go back and figure out what our length is, because they asked us for the dimensions. So the length equation was 10 divided by x squared. So L is going to be equal to 10 divided by 1.96 squared. So that's going to be about 10 divided by 4. So it should be about 2.5. I get more precisely, or more accurately, 2.6. So we've got 1.96 meters for the dimensions of the square on the end, and 2.6 meters long. So that's kind of a funny shaped drinking trough, but it'll have to work if they want to minimize their materials. Alrighty, so here's the your turn question. Now, take your time with this and have lots of fun. It's not very difficult, but it's definitely tricky. And if you get stuck, take a look at the solution. But I wanted to really challenge you this time. So have fun with that question. But I'm going to give you a hint. You're going to need 2 secondary relationships, because your first secondary relationship doesn't get rid of the variable that you want to get rid of. But you'll see when you get into this one, it's tough and it's fun. So have a lot of fun. It's an old problem that's been kicking around for a long time. So anyway, if you have any questions beyond the solution that's given right here now, so there's your solution. Or if you have any questions about any of this, don't hesitate to post your comments or questions on D2L. And if you have any issues with this stuff, it's the same procedures that we've been going through for all of our optimization problems. So ask any questions you want, and hopefully your studying is going well. All the best of luck on your exams, and thanks for listening.